Let's see if that works.
Yeah, I can't concentrate. Hey, yo, you want to get that?
Just takes off his jacket.
All right, guys, let's start doing some of these. 1A, there's a lot of different ways you could go. Somebody tell me one vector you created.
3 PQ. 3 negative 4. 3 negative 4 negative 1.
3 negative 4.
Negative 1.
Cool, I like it.
QR.
So I call V to QR. What'd you get there?
Negative 4, 1, and 5.
Did I do that one? Okay. What'd you get?
Negative 4, 1, and 5.
Oh, yeah. Anybody else got another one?
Negative 1, negative 4.
Say again?
Negative 1. Negative 3.
And that was what?
It's negative 1,
Negative
negative 3.
1? Yeah. Alright, I didn't do this one. So which one is that? It's going to be PR or RD? PR. PR. So what I always do for myself is when I have points, you can call it PQ, I just call it U, so it's quick to, especially if I give you one that's like, there's the points and then A through K. I'd rather just call them U and V so I can write it very quickly instead of PQ. But it's up to you. No matter what the hell you did, everybody should have gotten multiple of the correct normal vector. Does the length of the normal vector matter at all for this kind of problem? No. All I care about is the direction. So if the normal vector I got was 4, 20, negative 16, I would make it 1, 5, negative 4. Because that still points in the same direction. That's all that matters is the direction it's pointing in. Yeah, like it. Because when you set it up in the equation, you would be able to divide both sides by whatever you want to anyway. So the length of it doesn't really matter. Poor little dude. So, what do you guys get for the normal vector?
Negative 19, negative 11, negative 13.
I like it, so I just make it 19, 11, 13. Kabam! Because again, if that's the normal vector is the one you got here, well, I could also use that. I mean, that would be the same exact idea. You guys with me? A little bit? Okay. So then, how do I set up this equation? Now I've got, what are these? What is 19? A, B, C. So now my equation would be 19. Alright, so you can use, it doesn't matter which point you use. 19x minus 2 plus
11, x minus
y minus 1 plus 13 c plus 3. And what do you get when you solve for the other side? Yeah, I get, well, in this case you get 10. Because I divided by negative already. Is that what you guys got?
Yeah.
You might have gotten negative 19, negative 11, negative 10. And you just divide both sides by negative 1, right? Now you might realize why I ask you to take it all the way to this form. On the test, if I think about it, I'm going to say this, but because that makes it a hell of a lot easier to grade, because you can pick different points, you can pick different vectors. I got it. So if you put it there, it's easier to grade very quickly. Part B is so easy, some of you guys are like, I can't do that. But here's the idea. Here's the first part A, we did this. We have this little thing here, we said, here's my normal vector. Alright, it's right there, so it goes through the right points, right? And now I want the one that goes through the origin. It's still going to use the same normal vector, bless you, because it has to be parallel. Every plane parallel to this one has to have the same normal vector. Is that Think about it. Think about it. Try to come up with a contradiction to that statement. If I was parallel to this plane, could I have a different normal vector? Is that possible? No. The minute that's different, you're not parallel anymore. You have some angle to it. In fact, how do I find the angle between two planes? Is I find the angle between their normal vectors. So if they're parallel, they have to line up. Okay, let me let that sink in. So I have to use that same normal vector. And so part B becomes remarkably simple. Right? It's the same thing that I just did here, except instead of putting 2, 1, 3 in there, I'm going to put 0, 0, 0 because it's the freaking origin. Right? Still the same normal vector, but now it's just 19x plus 13. Where am I at? 11y plus 13z equals 0. I like it. Number 2 is also one that's easier than you first think. It's almost too easy to believe, and I don't know if you guys really believe it, but in order for that to intersect that, its x component must do what that one does. Its y component is z component, or you can think of it vice versa, right? So it really becomes a system of equations, because this guy says x of t equals t. X always equals t, so I'm going to plug a t in for x. What does it say about y?
0.
Y is always 0. So I'm going to make y 0. And what does it say about z? 2t minus t squared. Now, just to make sure you guys, part of the disbelief in that being that easy is it feels like you're always going to get an answer, but of course if they don't intersect, this is going to come out to an unsolvable equation. It's going to, do you see that? So it's still going to have a way to show you, oh shit, these don't intersect, dude. You just can't solve the equation. So then you plug it in for x, you get t squared, y is 0, and z is 2t minus t squared. So then you get 2t squared minus 2t equals 0. You want to factor this bad boy, please, dear God. Not picking on anybody, because I'm sure more people did this, but if you divide by t, if you divide by any variable expression, you don't have to identify yourself. If you divide by any variable expression, you lose the answers associated with that variable expression. So if I divide by t, I'm losing the answer of 0. Because what's the only way I can divide by t is if I assume t can't be 0. So I'm going to lose that possibility. So don't do that, poor little thing. 2t, so you get t equals 0, t equals 1, right? And now that's not good enough, of course. My question is what points? A very good point is that this is a vector function, but every vector points to points. So I wouldn't be so evil as to take points off. If you wrote it as a vector, I can understand why you would do that, but what are the points that where they intersect? For t equals 0, it's going to be 0, 0, 0. So they intersect at the origin. And t equals 1, 1, 0, 1. So it intersects those two, that curve intersects this paraboloid at those points. So you can imagine it would be paraboloid, and then this curve comes in, hits the poor little dude, probably on the way in and then on the way out, more than likely. Does that make sense? Whatever this curve looks like. Okay, so you could get no answer, meaning that here's a curve and here's a surface, and then my curve goes, no, I don't think so, and it just never hits. So you get an equation you can't solve. Or it could be one answer or two answers, or some finite number of answers, because I can have something that goes, and just hits it a lot of times. Or it sits on the freaking surface, so there would be an infinite number of answers. Right? My curve is on that surface. There's going to be an infinite. Where do they intersect? Every damn point. Infinite number of points. Okay. Number 3 is very similar to the ones we did earlier about the parametric way of doing this, right? So which one of these, it doesn't truly matter, but dear God, I'm always looking for this. Right? For parametric kind of situations, this is just screaming for you to use x equals what? Cosine t. If you want to rebel, you can make x equal to sine of t. It really doesn't matter. Y equals sine t. So then what's z got to be? And I think I heard somebody say this. I mean, if you just left it like that, I'm not going to take points off because technically you're right. But what is cosine squared by sine squared? Cosine 2t. It's one of those three options. Remember sine 2t? There's 2 sine, cosine. Cosine 2t is that asshole. It's got like 3 options. Oh shit, which one? All right, maybe. I just remember cosine squared by the sine squared, and then the other 2 are easy to remember off of that. Which you have to remember. Okay. So then let's put it. I want a vector function, right? So dear God, don't just circle these. Give me a vector function. So r of t equals cosine t, sine t. Either cosine 2t, or if you stop there and put that in there, you're fine. Okay, and we are headed into the taking derivatives and integrating vector functions. So I obviously want to take a second to make sure you remember some basic rules. The one that gives people the most trouble is the poor little chain rule. The people that misunderstand this so much, and when I first teach this to my 180 students, I tell them, write the rule before you do the differentiation. So what do I mean by that? Well, I know the derivative of sine of something is, what's that? Cosine of that thing times the derivative of the inside. That's the chain rule. So the people that don't write that, they make this mistake. I see this all the time. Y equals cosine. Let's try to write English up. There we go. Y equals cosine x squared 2x 2.
Oh, they keep going.
And they're just like, how do I tell how to stop? Mr. Waller, just don't do that. Look here. So here's the rule. Derivative of the outside function times the derivative of the inside function. Now, does this guy need a chain rule?
No.
Hell no. If you did use a chain rule, you would. What's the inside function is x. And what's x prime? 1. Shit. So you actually always use a chain rule just if the inside function is x. It just doesn't show up because it's times 1. Then we're like, gives a shit. So I don't need to use chain rule. That's how I know when to stop. So the question about when do I stop, Mr. Waller, tells me they don't understand the concept of it. You're just trying to memorize some kind of a process, and that's so good. So y prime equals 2x cosine x squared. And of course, what about this dude? The first thing I want to do is instead of a square root, let's make it a 1/2 power, and then y prime. Yeah, I've got to use chain rule and power rule and all this shit. So something to the 1/2 power does what? So there I am writing the rule, right? The outside function is the radical. I did its derivative, and then the inside gets a term. How are we doing? Yeah. So y prime equals. This will be negative 2x, right?
So it's negative x over.
So the negatives. So let's see. This negative 2x goes rid of the 2's cancel. So it'll be negative x over square root of 9 minus x squared. Like so like that. Yeah, it's going to. Is that cool? Now, obviously, if you write on the bottom 9 minus x squared to the 1/2 is beautiful. Just please do flip it. It's a negative power. And then one of my favorites for the most useless song that I've ever heard in my life. Now, listen, I'm not shitting all over the ideal business, but the more you do songs and mnemonic devices, the less connected you are to the idea. So this is remarkable. The idea of this is simple. When I first learned calculus, I hated quotient rules, so I just never did it. Not meaning I skipped those problems and got it out. I always rewrote this as a product. And the minute you do that once, I'm not telling you have to do, please, dear God, I'm not saying do this. But which one of those is going to have a minus sign on it because of its derivative? So I'm going to do the derivative of 3x is 3 times that business, plus 3x times the derivative of that. Well, it's going to have a negative, isn't it? So the minus sign is when I take the derivative of the bottom. Then the whole thing makes sense. That's why there's a minus sign in the quotient rule, because the bottom has a negative power. Shit. That's all. So my song is top first. And that's it. If you do the top first, so what do I mean by that? You can either do the bottom first, minus the other. No, so it's top first because it's going to be minus when I do the derivative of the bottom, because the bottom has the negative power. Now, if you enjoy your song, I'm not taking it away from you, whatever works. But they should never have taught you that damn thing. They should have just taught you the idea more importantly. So either way you do it, what do you get? We're going to get y prime top first. Take derivative of the top first. 3 times the bottom. Why is that minus sign there? Because that negative 1 would come down and make it a minus. That's why. And then it'll be 3x times the derivative of the bottom is 1. Over the bottom squared. So then you get 3x plus 3x is gone. 3x plus 15. Bam. Coolness. Coolness. Okay. So let me see. I think maybe I should just keep going with this here. Yeah, I like it. So guys, a couple of new things. This test is officially going to go up through 13.2. So if I remember correctly, I think I put 13.2 on website this morning. So just through 13.2 homework will be due. We'll do 13.3 and the rest of it for the next test. A couple things you got to finish up in 13.2. We actually barely did 13.2, but all right, guys, is it cool if I write this? Or do you understand if I write this like this? This is what x is, x is equal to f of t, so forth. So when I do limits, we talked a little bit about limits. The limits is going to carry through each component. So this is called inheriting properties. When each piece is a real valued function, so therefore I'm going to inherit all the properties of real valued functions. So derivatives are going to be stupid simple because just to show you the idea of what this would be theoretically and then what it really is. Just to remind you that you can have the d by t notation. So this would be the limit as h goes to 0 of r of t plus h minus r of t over h. Ooh, that's awesome. But thankfully, I'm not going to put you through everything you went through on 180 because I would just take this idea and basically it would distribute in a way through to each one of those. So this would be the limit as h goes to 0 of f of t plus h minus f of t over h, comma, and so forth. You guys get the idea. So it is exactly what we would hope it would be. The derivative of r of t is just going to be the derivative of each piece, each component. Thank God, because they inherit the properties that they have. So that's just equal to f prime become a, oh, forget Jeff here. All right. Few years away from total not being able to write at all. Okay. All right. So that's the derivative of a vector function. What would that be, obviously, if this was a position function of some particle? Velocity. This would be the velocity. I like it. And specifically, this is the velocity because this has what that velocity needs. That's different from speed. Direction. So what would the speed of this thing be? Yeah, I like it. So there's a difference between these two, obviously, hopefully, and we'll see how those are used differently. But for right now, we're not even calling them particles position. We're not talking about position, velocity. There's a whole section that does that, which is really funny. It's just a repeat of this, just with more direct applications in kinematics and motion. Okay, where do you want to go next, Jeff? I don't know. Oh, this is also called, this guy here is called the tangent vector, which should hopefully be making sense. If I found this, let's do a problem real quick here. If I said find the equation of the tangent line to some vector, just to give us a little hint for the future. Find the equation of the tangent line to RT at some point. Can you start to piece together how you'd be able to do that? I mean, what do you need for the equation of a line, period?
Slope.
So slope meaning direction vector, right? So slope, I know what you mean, direction vector, right? The V. And some point. So they give you a point. How to find this guy's V? How to find the slope, the V? Take the derivative of R and then do what? Plug in the t associated with that point, right? Because I want to know at that point. So how do you find the derivative of a function at a point? You take the derivative and then you plug that information in. So you're at that point. Does that make sense? Same kind of thing would have to happen here. All right. So that's the tangent vector. We did talk about unit tangent vector. We did talk about that before. That was represented by big ass T. Now hopefully, even if you forgot how to get this, I've got the parts we need there. How would you get the unit anything vector? Yeah, you would take, yeah, I like it. You would take the vector itself divided by its length. Cool. So that is the unit tangent vector. Again, unit vectors are remarkably useful because then you can use them to build. Then you make them any length you want to very easily. We're also going to use this in a few further theorems and formulas in the future. Let me see, what else did I want to throw out here? Oh! Let me flash this at you here. Do these look familiar?
Wow, what are those?
What are those?
Derivatives. They're just derivatives.
So, do you see these three here? So this is kind of like, notice how this is a dot product, this is a cross product. What's happening here? At any specific value of t, what is this physically?
Scalar.
Scalar, I love it. So it's just the scalar times, so scalar multiplication. So you gotta be careful when you say multiply scalar, you gotta be, so scalar multiplication is valid all day long. So it's meaningful. This should sound familiar as a homework problem. If I try to do scalar dot a vector, doesn't make any sense. Because dot product is defined for two vectors, right? But I can do scalar multiplication of vector all day long.
What is this?
So,
What about number 2? When it be the same?
but the difference between these two is that's a constant. That's a constant. So if I have, what's the derivative of 2x squared? 4x. The 2 just came for the ride, right? So that's the c comes for the ride. Here, why is this different? Because this is going to use what rule? This is a function of t. That's a function of t. Going to use product rule, right? Derivative of one times the other plus that one times the derivative of the other one. I mean, that's the product rule. Hey, look at this one. That's the freaking holy shit and a half. This one happens to be. Oh my God. So, whatever version of multiplication, this is remarkably nice and nothing that you should expect. This should not be expected. But any multiplication we use, the derivative of that is going to be related to the product rule. I mean, that's too beautiful to believe for a second, but it's true. Yeah, let it be awesome. And then this guy, of course, they tell you what that is, so it's a giveaway. Right? There's a vector function of with some other function inside of it, so therefore you gotta use good old chain rule. Oh shit. You thought it was your chain rule, you're so wrong. And then my hope is look. No. You guys are so funny. Do you remember how many pages were devoted to this thing in your 180 book? So many pages. And then you had to actually, hopefully you had a good teacher again, I keep saying that. You had to actually do some of this Riemann sum stuff with the I stuff. Remember, that's the sum of I squared and sum of I cubed. Oh yeah, because then you can really see what goes into creating an integral. The idea of being the area. This is the only thing. This is the only place you'll see that here. We're not, because we've inherited. You've already done the work in 180. See, that gets applied to each component, and each component operates the same way we know they do already from Math 180. So now I can just go straight to the integral of a vector function is the integral of each component. And again, what are we trying to do? How do we get from r of t to r prime of t? We took the derivative of each component. What is this trying to do? Go back. Right? It's trying to recover what it came from. What was this the derivative of? So of course I'm going to undo to each component what was done to each component. Integrate. Does that make sense? Look at, please, does that make sense? Look how little room they give to this idea of integration. Because you've been integrating for so long. So you should know how to integrate. Okay. So a little look to the future. Whoa. Alright, this is section 13.3, but this is where we'll be doing. See here, that what is this in here? That's the length of the velocity, which is also known as the speed. Right? So it's interesting. So if I want to know the length of a curve in space, I integrate the derivative, which sounds kind of backwards, but we're going to build on why that's true. But maybe this looks familiar to some of you guys. Arc length formula. That's so funny. You should have made exactly as much noise because that's the same damn thing if you think about it. What is the length of r prime? It's going to be x prime squared plus y prime squared plus z prime squared is in 3. Now look. That's what the hell it is. Holy shit. Which is what you guys learned before. It's the arc length formula. Again, surely makes sense because it's freaking arc length. So, it's just we can now write it in a better format, a more compact format. Alright, well, that's plenty. Where are we at? Yeah, let's leave early today. Sounds good. Is everybody okay with that?